Hey guys. All right, so we are going to do a lesson today, which is 3.1.1, and we're going to use an area model, and we're going to be discussing how I can represent it. At this point, you should have a couple things out. Obviously, a pencil. Make sure that you have a calculator and a sheet of paper. And you should also have this sheet of paper along with you, so make some notes along the way. So follow along as I read what's going on. So in the previous courses, you studied the probability, in which probability is the measure of the chance that a particular event will occur. In this section, you solve probability problems that require you to analyze more complicated situations of chance. The next two lessons focus on tools for listing all the possible outcomes of probability situations, and we call that the sample space. So go ahead and underline or highlight that word, sample space. All right, so let's get to the first question. It's in the genes. Can you bend your thumb backwards at the middle joint to make an angle, like in the example at the right? Or does your thumb remain straight? So if I take my thumb, that's how I bend it. Notice that mine kind of remains straight. The ability to bend your thumb backward is thought to rely on a single gene. Well, what about your tongue? If you can roll your tongue into a U shape, you probably have a special gene that enables you to do this. Assume that half the US population can bend their thumbs backwards, and that half can roll their tongues. Also assume that these genes are independent, meaning, in other words, have one gene does not affect whether or not you have the other. And randomly distributed, which means it's spread out throughout the population. Then the sample space of these generic traits can be organized in a table like this one below. So if you take a look at your problem down below, you can see kind of this table. I'll zoom in a little bit. So we see the bend thumb. So yes, I can bend it. Half the people can. No, I cannot. Half the people cannot. Can you roll your tongue? Half the people, we said, can. Half the people cannot. So what I want you to do is I want you to pause the video right now, and I want you in your groups to discuss these first three questions, right? So you guys can read the first three questions on your own, and then pause the video, and then we'll come back and we will talk about them. All right? Press pause now. Alrighty, so you have undo the pause button. So let's talk about the probability of all of this stuff. So let's look at our first question. So it says, according to this table, what is the probability that a randomly selected person from the United States has both of these special traits? So we want to know what is the probability in that box. That is, what is the chance that a person, he or she, can roll his or her tongue and bend his or her thumb backwards. So that and is really important. So if you think about what we've talked about before about area models, if this is a 1/2 and this is a 1/2, in this box, what you're doing is you are multiplying the 1/2 by the 1/2, right? And if you do that, you multiply straight across, you're going to get a 1/4. So the two yeses, right, if you can do both, has a 1 in 4 probability of happening. So we could say 1/4. Now we want to convert that to a decimal, so that way we can convert it to a percentage. So if you have your calculator and you need to divide 1 in 4, you're going to get that it's 0.25. And percentages, if we multiply everything by 100, we're going to say that 25% of the population can roll his or her tongue and bend his thumb backwards. All right. So if we have some difficulty and your group doesn't understand, press pause and we'll come and help you. So let's look at the second question. According to the table, what is the probability that the person has only one of these special traits? We want to justify your conclusion, right? So it means that it just has one. So if I look at these two boxes, right, that means I can roll my tongue, but I can't bend my thumb backwards. So again, I'm going to find out that it's a 1/2 half times 1/2. So it's a 1/4 probability, right? Or can I bend my thumb backwards, but I can't roll my tongue? So again, 1/2 times 1/2 is equal to 1/4. So what we want to do is we want to add those special traits up, right? Because it could be either one of these. We can either be in this box or that box in order to justify just having one of those special traits. So if I add up the 1/4 with the 1/4, common denominator is a 4. So we get a 2/4, which breaks down to 1/2. What is 1/2? It's 0.5. So that means 50% of everybody in the world, based on this data, can either do one or the other. That's what that means. So if we look at the next question, right, this table is useful because every cell in the table is equally likely. Therefore, each possible outcome, such as being able to bend your thumb but not roll your tongue, has a 1/4 probability. And again, we didn't fill this box out, but if you look at it, 1/2, 1/2. So if I multiply those together, I do get a 1/4, right? However, this table assumes that half the population can bend their thumbs backwards, but in reality, only about 1/4 of the U.S. population can bend their thumbs backwards, and that means 3/4 cannot. So it turns out that a lot more than half, about 7/10 of the population, can actually roll their tongues, right? So what we want to do is we want to figure out why this happens. So let's go ahead and look onto the back of our paper. All right. So let's justify what actually happens, right? So one way to represent this is with a sample space that has outcomes that are not equally likely. And we use a probability area model. So again, we've seen area models back in Integrated 1. We're going to use it with probability. Again, it's bolded, so let's underline that, highlight it. An area model uses a large square with an area of 1. So that means I could add up all my numbers into my box, and I would always get the number 1. Okay. So let me reiterate a couple things. So flip it over back to the front side. So let's look at this box right here. So I have a 1/4, a 1/4, 1/4, 1/4. So if I add, oops, can't see that, sorry. If you add up the 1/4 4 times, so box 1, box 2, box 3, box 4, and again, common denominator tells us that we can add the numerators up. So 1 plus 1 is 2, 2 plus 2 is 3, 3 plus 1 gives you 4. And notice 4/4 gives us 1, right? So no matter what area model we're talking about, it will always add up to the number 1. So let's go back to the back side and let's talk about this question. Okay, so the square is subdivided into smaller pieces to represent all the possible outcomes in this sample space. The area of each outcome is the probability that the outcome will occur. So for example, if 1/4 of the U.S. population can bend their thumbs back, then the column represent this ability should only take 1/4 of the square's width, as shown on the right. So notice that here's the 1/4, so very smaller compared to what we had earlier. And then the rest gives you, the rest of the population is no, and that's 3/4. Okay? So for example, can bend then the column, yes, we've already read that. So how can the diagram be altered to show that 7/10 of the U.S. can roll their tongues, right? So again, we're going to copy this diagram. So if you think about 7/10 can roll, that's a huge number. So that means we want to break this up into yes. So I'm going to put a little y for yes. And then this will be 7/10. Right? Now, what's the remaining people that can't roll their tongues? Well, we want to add up to 10. So what is 10 minus 7? You got the no's at 3/10. Okay? So what I want you to do is I want you to go ahead and I want you to pause this video, and you're going to go ahead and you're going to try to answer both B and C. My suggestion is to fill in the chart. Leave it as fractions. Your life will be a lot easier when it's fractions. So go ahead and pause the video right now. Press pause now. All right. So you have figured out And let's talk about it now together. Okay. So what we want to do is let's go ahead and fill in our chart, right? So I'm going to go ahead and multiply the 7/10 by 1/4. So again, I can multiply straight across. So 7 times 1 is 7. 10 times 4 is 40. And I'm going to do the same thing over here. So 3/4 times 7 over 10. So this will give you 21 over 40. And then 3 times 1 is 3 over 40. And then 3 times 3 is 9 over 40, right? Let's prove that it all adds up to the number 1. So 7 over 40 plus 21 over 40 plus 3 over 40 plus 9 over 40. So 7 plus 3 is 10. 10 plus 21 is 31. 31 plus 9 gives you 40 over 40, which in fact gives you 1. So again, it's always good to understand that. So let's look at our question now. Zoom down. So the area of the regions represent the relative probabilities for the different outcomes. For example, the proportion of the probability area model representing people with both special traits is a rectangle with a width of 1/4 and a height of 7/10. What is the area of this probability? Well, or this rectangle, I should say. You've already solved that out when you filled out the rectangle. So what's the area? You should have written 7 over 40. And if you plug that into a calculator, that gives you 0.175. So it's 17.5%. Okay, so what does the area model mean in terms of the two traits? That means that if a person is randomly selected, they have a 17.5% chance of having both of these traits. Okay, so now what we want to do is what is the probability that a randomly selected person can roll his or her tongue but not bend his or her thumb backwards? So we want yes to rolling the tongue. So yes to rolling the tongue, but no to bending the thumb backwards. Boom, we're at that box. So it'll be a 21 over 40, which in your calculator, if you calculate that, should be 0.525, which is 52.5%. Okay. So if you need to pause it to copy down some more stuff or change your answers, please do so. If not, let's move on to another problem. Okay, we are talking about being shipwrecked. Are we talking about shipwrecked or that? That's on that paper. 1 second. Difficulties at the bottom. Other paper that you just took away. My Vanna White is helping me out. Okay, so we are on not shipwrecked, so we're on problem 3 first. So we're talking about probabilities in vain, right? All right, you and your best friend may not only look different, but you may also have different types of blood. Ooh. For instance, members of the American Navajo population can be classified into 2 groups. 73%, or aka 73 out of 100, have an O type, while 27%, aka 27 out of 100, has an A type. So what I want you to do is I want you to pause the video and I want you to fill out your box and try to answer these 2 questions, and we'll come back and we will talk about it. Ready? Pause your video. All right, so let's talk about this. So we said that, so 73%, so 73 out of 100. It's a little hard to read on this paper, but you should be able to read it on your paper. So that means, yes, they have it. And then that means 27 don't have it. They have the other one, they have A. And on this side, the same Navajo number 2. So we can go ahead and when you multiply your percentages together, so 73 times 73 over 100, you should get 53.29% for the OO box. In these two boxes, right, since they are the same, it should be 19.71% in both of these boxes. And last but not least, if I multiply 27 by 27 all over 100 times 100, it'll be 7.29%. Again, take a moment with your calculator. You should have added up all of these numbers, and it should give you 100%, and which is the same thing as saying like it's 1. So let's answer. These questions. So we've already figured out our area model. So now we want to know what is the probability that 2 Navajo individuals selected at random have the blood type A. So what is the probability that they have the same blood type? So, excuse me. So we want to know if they have both somebody with both the blood type. So we can say probability, can't read that. So we'd say P of both A. What this means is that this is your bottom right box, right? So notice your bottom right box is right here. Both Navajo 2 and Navajo 1, they're both A, so that would be that percentage. So we can say, we can approximate that both probability is about 7%, right? If we want to be exact, right, we found out that it was 7.29%, okay? Okay, so basically you can have it be either approximate or exact. So now we want to know what is the probability that you will have the same blood type. So if we take a look, you can either have both AA or you can have both OO. So when I say I want to know, I'm going to add the 53.29 because that is my O blood type. And then this will be the 7.29 because that's my A blood type. So again, if we approximately add these numbers together, right, you're going to get about 61%, right? So if we want to be exact and we add the 53.29 with the 7.29, you are going to get an exact answer of 60.58. So that's why we rounded it up to 61. All right, so now let's take a look at shipwrecked. So the shipwrecked one is this one right here. So Zach and Nick, both from Vermont, are shipwrecked on a desert island. Zach has been injured and is losing blood rapidly, and Nick is the only person around to give him a transfusion. Unlike the Navajo you learned in the last problem, most populations can be classified into 4 blood types: O, A, B, and AB. In Vermont, approximately 45% of people have O blood type, and so forth and so on. So you guys can read all of that. While there are other ways, right, this problem only considers these 4 types of blood types. So let's go ahead and pause the video again, and I want you to go ahead and fill out this chart, leaving it as percentages. So if you multiply 0.45 by 0.45, figure out what that is as a percentage, and you're going to fill out all of the boxes. Once you've filled out all the boxes, try to answer question B and question C. So go ahead and pause that right now. All right, so back, and if you filled out your boxes, you should have the following numbers. This should be about 20.25%. This one will be 18%. This one's about 4.95%. This is 1.8%. Up here is 18%, 16, 4.4, 1.6, and 4.95. This should have been 4.4, 1.21, 0.44. Can't really read that one. Try that again. So 0.44. This is 1.8, 1.6, another 0.44, and a 0.16. I forgot percentages on the symbol on all of these, but hopefully you did not. Okay, so the first question is, what is the probability that Zach and Nick have the same blood type, right? So again, I can write it as probability of same blood type, right? So I want to look at my boxes and I want to see where they're the same. So OO is the same, so 20.25. And then I'm going to add that up with AA. So AA is 16%. If I add that up with BB, that would be 1.21%. And then AB with AB is 0.16. Right? So if you add these up in your calculator, you should get 37.62%. If you want an exact answer, if you want the approximate answer, 62 would be rounded up. So you're approximately at 38%. Okay. Well, guess what? Luckily, two people do not have to have the same blood type for the receiver of blood to survive a transfusion. Lucky them. Other combinations will also work as shown in the diagram at the right. Assuming that the blood is compatible in other ways, a donor with a blood type O can donate to receivers with O, A, B, or AB, while a donor with blood type A can only donate to A or AB. A donor with B blood can donate to a receiver with B or AB, and AB can only donate to AB. So assuming that Nick's blood is compatible with Zach in other ways, we want to determine his probability that he has the type of blood that can save Zach's life, right? So what we want to, I think what we are, we're assuming that their blood is compatible in other ways. So we are going to be adding some numbers up. So we want to add up all of the O column, right? Because the O is compatible with everybody. So if I add up 20.25 with 18, can't see that, excuse me, 4.95 and 1.8, this is all so far in column O. And then what we want to do is we want to continue, and we are going to add up the A to A and the A to AB, right? So the A to A is 16%, and then 1.6. Can't see that decimal. 1.6, and then we're going to add up in the column B to B column, as well as the B to AB column. So plus the B to B is, what is the B to B? 1.21% plus 0.44%. And finally, the last column that could potentially is the 0.16. So that's your AB to AB. So if you add up all of these numbers, you are going to get an exact answer of 64.41%. So this one's under a 0.5, so this is approximately 64% that assuming Nick's blood is compatible with Zach's. So he's a 64 chance of saving his life. That's awesome. Right? So you made a critical assumption in this last problem when you make a probability area model and multiplied the probabilities. Blood type is affected by genetic inheritance. So what if Zach and Nick were related to each other? What if they were brothers or father and son? How could that affect the probability outcome? What has to be true in order to assume a probability area model will give you a very accurate theoretical probability? So go ahead and talk to your group members, pause this, and see what you guys discuss. Okay? So, so let's take a look at these questions. So the first question is, what happens if they're related to each other? Well, if they're related, then we know our random samples, that our samples are not really random from the overall population because they are related. Their probability of having the same blood type is much greater than a random population, right? So your chance of having the same blood type as a family member, brother, sister, aunt, uncle is very high versus the person sitting next to you. So that means that knowing Zach's blood type could impact the probabilities in this table in a different way. So the outcomes are not independent. So for the second question, what has to be true in order to assume a probability area model will give an accurate theoretical probability? Well, we have to make sure that the outcomes are independent. So there's nothing else that is affecting our outcomes, essentially. Okay? So that is the end of 3.1.1. Go ahead and wrap up this, and you will be watching 3.1.2.